Hello everyone, my name's Brian. I'm a mathematician. I work on a project called SideEB, and I'll tell you a little bit about some interesting financial applications that you can apply SideEB to. This talk will be slightly different than what you've been hearing, more geared towards back-end technologies than consumer or front-end facing things. SideEB is an open source database that organizes data in arrays that are distributed across Linux clusters. It's horizontally scalable and it has a very conservative consistency and durability model. It's fully ACID. And the project is led by Mike Stonebreaker at MIT. The project began about 5 years ago as a science project, a combined government, academic, and industry consortium to manage very large-scale scientific projects, mostly in astronomy and remote sensing. But today it's used widely in genomics. Perhaps our most high-profile application is the 1,000 Genomes project at the National Institutes of Health, which is managing upwards of many, many hundreds of terabytes of data and has online web applications and lots of cool things like that, all running on SideEB. So I'll give you a little bit of background about SideEB and then quickly show you one interesting application on Bitcoin that I've been working on. Unlike traditional relational database models or table-based ways of organizing data, array selections, this picture illustrates how you might select data for a 2x2 array in a relational database. SideEB organizes those same data in the same form that you would compute with them mathematically as an array itself. So data are represented as n-dimensional sparse arrays in the system. And that leads to all kinds of benefits, especially for scientific and linear algebra applications. But most importantly, data that are stored next to each other in the coordinate system are stored next to each other in your network. So there's a natural user-defined spatial clustering of data in the system that severely reduces the movement of data across the network, which for many terabytes of data is a very important objective. Data in SideEB can be sparse or dense, and it's an obvious natural fit for large-scale distributed linear algebra applications. And most importantly, for end users, we're trying to make the system very easy to program from Python and R, which are two very widely used languages in science these days. Onto an interesting application that I've been working on that has some application in finance. One way that you might look at graphs, for those of you who are familiar with network theory or graph analysis, is like this, or an equivalent representation is as a sparse matrix. So these two pictures show the same data, just organized differently. These data here can be directly stored in a SideEB array. A particularly interesting graph that I've been looking at are the Bitcoin transactions. This is a slide represents a big simplification of what's really going on in the blockchain. But essentially a transaction consists of an exchange of Bitcoins from an address to another address. And that can be represented as a directed graph, which in SideEB would be a sparse matrix. It's not that big of a matrix for our scale, but we'll look at an example result in a moment. What are questions that you might ask of graphs? One particularly interesting question is to identify the most important nodes in a graph. For some definition of the words most important. One of those is subgraph centrality, which is a technical thing that I won't get into on stage here in 6 minutes, but the mathematics of which I'm happy to discuss with you if you come by and talk to me. Very recently, there were some interesting methods implemented by the fellows listed on the slide here, and we implemented them recently in SideEB using SideEB's sparse linear algebra capabilities. These are kind of cutting-edge algorithms that dramatically outperform other available techniques for answering questions like this. And this is a particularly computationally intensive problem to solve using those other methods, but much more efficient using those methods. To give you an example, you might ask, what are the 5 most important nodes in the Bitcoin transaction graph? Maybe you would expect to see Mt. Gox a year ago before Mt. Gox imploded, or some other well-known identifiable addresses. Maybe some of the addresses that you don't know about are not identifiable. This particular graph is a year-old Bitcoin data. For SideEB standards, it's very small. It was only a 6 million by 6 million sparse matrix with 16.3 million non-empty cells. And we can answer the question posed here in just tens of seconds on a regular workstation using SideEB, which may not seem very impressive, but it's a difficult result to compute otherwise. SideEB can do lots of other really interesting things suitable for financial applications, even though it was originally designed for science. Some of those are listed here, and people are actually using them in production systems in computational finance right now, including decimating data on regular time intervals, doing what is often known in the finance industry as of joins, or kind of temporally inexact joins on data, processing vast amounts of tick data. If you're working with lots of tick data, as you know, it can be many terabytes of data, as well as higher level math functions like machine learning algorithms, principal components, large correlations, and generalized linear models. My colleague Bill and I are down at a booth downstairs, and for details on the algorithms that we used in these graph analysis methods, feel free to talk to me if you'd like to talk some mathematics, or if you're interested in processing terabytes of data with an ACID database, talk to me or Bill anytime today or tomorrow. Thank you.